The kinetic energy of an object is the energy that is associated with its motion. We're going to learn that there is a relationship between potential and kinetic energy and how one of them will give rise to the other one. And in some cases, they actually end up switching off and feeding each other. So by definition, kinetic energy is 1/2 mv squared. Okay. Now, if we look at the units, you'll see that this is a kilogram, and this is velocity squared. That's a meter per second squared. That means I have 2 m's and 2 s's. What you'll notice is this is a kilogram meter per second squared, which is a Newton. And once again, we have a Newton meter. A Newton meter, by definition, is a joule. Now, for those of you that are wanting a nice little exercise, I would suggest to you in your left columns to prove that kinetic energy is 1/2 mv squared. No need to, but those of you that are looking for A-level understanding, you would do this by using the third kinematic, and you would be using Newton's second law. So you would use Newton's second law, and you would use the third kinematic on the x-axis. You would, substitute, replace, move things around, make some assumptions, and then you're going to get some fascinating things. You will also need to use the definition of work. Okay, so if you want to prove this, you're going to need Newton's second law. You'll need to use the third kinematic, and you'll need to use the definition of work. It's a good challenge for you. No need to do it, but it'll definitely give you some great understanding. We have a mass of 2 kilograms and a velocity of 3 meters per second. A lot of people forget this squared. Make sure you have this squared and only the velocity is being squared. If you were to put this in the calculator, you're going to go ahead and get 9 joules for this. Don't forget the squared. Again, we put this in the calculator, do it at one shot, get the correct answer. Doing this, you're going to get 500 joules. You would recall that the unit for work was also a joule. Interesting. Let's get a bit more complicated. The velocity. So if I have the mass and I have the energy, let's find the velocity. To do this, we want to get the v by itself. This 1/2 is in the way, so I want to multiply both sides by 2. That's the reciprocal. That gets rid of this 1/2. Now we would divide by the mass. We would square root both sides.
I think I need a hug.
And this is the relationship between the velocity and the kinetic and energy and the mass, where we are actually finding the velocity. Plugging these numbers in is no big task, but keeping track of the units is a big task. So let's look at this carefully. We have 200 joules over 0.5 kilograms. But a joule is a Newton meter. And a Newton is a kilogram meter per second squared. What happens is these kilograms cancel out, and we're left with a meter times meter, which is a meter squared over a second squared. If I put this in a calculator, I'm going to get approximately 28.28. But look at what happens here. If I square root the m squared, I get an m. If I square root the s squared, I get an s, right? This is essentially this right here. And I can split them up. and it ends up resulting in an m and an s. So our velocity for this object experiencing 200 joules of energy ends up being about 28.28 meters per second, and I did round that.
Great job, everybody!
If an object is not moving, does it have kinetic energy? Explain. These three objects, and they're going around in different directions. What would be the total kinetic energy of the system? Well, energy in a system actually ends up adding up, all right? So even though they're going in different directions, the energy is definitely there, all right? Think about kids in Chuck E. Cheese, or kids in Disneyland, or kids at a park, okay? It doesn't matter if they're going in different directions, the energy is there, okay? So, what we could do is, instead of, we could do this a few ways. We could find the kinetic energy of this first object, and then of the 2 kilogram object, and the third object, and add them all up. But the reality of it is that they all have the 1/2, and they all have the same velocity squared. So we could simplify this by just adding up the masses, and then multiplying by this velocity squared. Don't forget, the whole thing is squared. Important. You can expect me to ask you questions about this many times, including the test.
I want to have them answered immediately.
If the mass of an object is doubled, how does it affect the kinetic energy? So here's kinetic energy is 1/2 mv squared. But what I'm proposing to you is this. If I instead do if I'm double the mass, right? I'm doubling the mass. That means I'm going to 2m. In order to keep this balanced, right, you'll notice that I have put in black the original formula, 1/2 mv squared. This extra 2 is here because I doubled the mass. In order to keep this balanced, I would have to double the kinetic energy. What I'm proposing to you is, if I double the mass of an object, I end up doubling the kinetic energy. Let's try this again. What if this time, however, I doubled the velocity? Does it end up doubling the kinetic energy? Well, if we take into account that this is being squared, right, this essentially means that each of these gets a second power. Or if you're not comfortable with that, squared means I would multiply this by itself twice, giving me a 4v squared. So this ends up becoming a 4v squared. Again, you'll notice that I have the original in black, right? 1/2 mv squared. But this time I have an extra multiple of 4. So if I were to double the velocity, I would end up quadrupling the kinetic energy. Folks, please, 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 please. You know, many times in this class we've talked about death, right? Well, spoiler alert. If you are speeding, if you are going twice as fast as the speed limit that is posted, your impact energy is not going to be simply twice as much, it'll be quadruple. It'll be 4 times the amount. What if you were to triple your speed? So rather than going 30 miles per hour, you're going 90 miles per hour. You would end up having 9 times the impact energy when you collide with an object. Okay, so this idea of speeding is extremely dangerous because of physics. Okay, when it's not just a matter of I'm going twice as fast, so it's going to be twice as bad. No, no, no. Twice as fast, 4 times as bad. 3 times as fast, 9 times worse. 4 times, right? 16. And that's because of this squared. This squared has a huge impact on the kinetic energy, this velocity. So you messing with the velocity, right, is going to really mess with kinetic energy.
I think I need a
Okay, on a
hug.
happier note, what if we did the following? What if we halved the mass, but we doubled the velocity? So we halved the mass, we double the velocity. Well, we know what happens here. That was part B. So it's going to be 4v squared. And here's a 1/2 from the mass, because I half the mass. But you'll see that this 1/2 and this 4, they cancel out. Again, you'll notice that this is the original equation right here, right? 1/2 mv squared. So by me doubling the velocity, I've quadrupled the kinetic energy. But because I halved the mass, that means that I half the 4, and it only ends up being doubling kinetic energy. So part C, if we half the mass and we double the velocity, we actually only end up doubling the kinetic energy. Part D, can kinetic energy of an object ever be negative? Well, let me ask you this. Can the kinetic energy, it's affected by two things, the mass and the velocity. Can the mass ever be negative? So on that account, kinetic energy will never be negative because the mass will not be negative. However, can velocity be negative? We've seen that before. Velocity can be negative, but it's being squared. So even if my velocity were negative, right? Let's say I have negative 3 meters per second. If I square it, it ends up becoming a positive number. So the kinetic energy of an object can never be negative. The velocity could be negative, but because the formula has a squared, it automatically makes it a positive value. All right, in summary, what properties affect kinetic energy?